Hey everybody, let's go over problem number 2 in this classwork/homework thing. And so my suggestion to you is to use this video as an answer key and then try to work through the problem and then see what I do. Not only to see if you have the right answer, but maybe even more importantly to make sure that you're thinking about the problem right. And in this case, I really like this problem because we're not necessarily dealing with grams. We're dealing with liters, so we're dealing with a volume of a gas. Okay, and I kind of really like that. So let's get started on some of this, and then we can see what we get for an answer. Okay, so just so you can see what I wrote here, it just says, remember that 1 mole of gas occupies 22.4 liters at STP. So I'm going to put the calculator up a little higher, and now we get to go. Okay, so it says write a balanced chemical equation for this process. Make sure we include states. So now we're going to go here, we're going to go sulfur hexafluoride, SF6, and that decomposes into its elements. Now there's a lot of information trapped in there because it decomposes, so that means we know that that reacts because we know what decomposition reactions are. We may not know exactly what it decomposes into normally, but it tells us that it decomposes into its elements. So it's going to decompose into sulfur and fluorine, and not only that, we know that fluorine is diatomic. It's part of that Hankel-Briff thing, okay? And so that's the start, that's kind of the bones of our chemical equation, chemical reaction, but we need to make sure we include states, and we need to balance this guy. So let's include states. SF6 is a gas. How do I know that? Well, 2 things. It says gaseous right here, and that's the obvious. But in terms of thinking about this, because it may not be there, the idea is this is a covalent compound, and it is a nonpolar covalent compound. So SF6 has only London dispersion forces. London dispersion forces are weak, and therefore SF6 is probably found in nature as a gas. Okay. Now, in order to do this, sulfur is a solid. You can use the periodic table for that, and fluorine is a gas. Elements, you can look at the periodic table, and you can find out if you have if they're a solid or a gas. Okay. Now we have to balance this. Now, for every sulfur here, there's 1 sulfur, and then there's 1 sulfur. Now for fluorine, though, I'll balance in blue. Okay, fluorine, there's 6 here. So 6, there's 2 here. So I need a 3. I need to put a 3 there. Okay, so for every one of these, we make 3 F2s. Okay, so that now completes what we needed to do for part A. The next thing that we need to do is determine how much we're making in moles. So we're going to write our ICE chart. Notice I'm going to do this in 3 columns. And when I do this in 3 columns, I'm having 1 column for each thing in the reaction. Okay, I'm going to go ICE. Okay, and now what do we have going on? Okay, is that we have, I'm going to put this in green here, we have 5.83 liters of a gas. Now, we know that ICE charts are given in have to use moles as our unit, so we have to convert liters to moles. How do we convert liters to moles of a gas? Well, guess what? We can use our conversion factor that we have 1 mole is 22.4 as long as the gas is at what we call STP, standard temperature and pressure. And it is. So we're going to X-line. Okay, rule number 1 of any ICE chart is to X-line, or is to convert to moles, not to X-line. You're probably going to X-line anyways, but okay, so we have 5.83 liters of SF6, and we're going to X-line it, and we want to go from liters to moles, and so we have 1 mole is 22.4 liters. Now, we go and notice that liters cancel out, and now we're going to calculate our answer, and we type 5.83 times 1 divided by 22.4. Now, if you can skip over the multiply by 1 thing, that's fine. If not, okay, whatever. But either way, you're going to get the right answer, and the answer is 0.260 moles of SF6. Okay, so if we have SF6, if that many moles of SF6, that's going to go right up here. 0.260. I don't have to put the unit there because it's assumed to be in moles. Now, we have to do some other things, and once we get this, what we can do is we can fill in some zeros here. This reactant, because there's only one of them, this reactant is going to get used all the way up, and it's going to go down to 0. We're going to then have zero products for a couple of reasons. First of all, if we're making this in a reaction, typically we don't do reactions unless we don't have any and we want to make the stuff. And so that's kind of the logical way. But then if we look in the problem, you'll notice that it doesn't mention anything about sulfur or fluorine and how much each of those, how much we have of each of those. So if it's not given, assume that it's 0. Okay. Now we're going to do this. We're going to figure out the change box here. The first change box is kind of the key to the rest of the ICE chart. So 0.260 to get down to nothing. That means that the reaction is going to use up all of the SF6. Perfect. Okay, but that change box here is phenomenal because that's going to allow us to calculate this and this, which then gets us down here. Okay, so we're going to use this value in the change box because it's a ratio. However much of this is used up will tell us how much of this we're making and how much of this we're making. So I'm going to go down here, and I am going to start, and I know that we have 0.260 moles of SF6, and we're going to X-line it. And now what we want to do is we want to convert SF6 to S. And in order to convert that, we need to use the balanced chemical equation. The balanced chemical equation shows us what the mole-to-mole ratio is. Notice I say mole-to-mole. Shows us what the mole-to-mole ratio is of one thing in a reaction to another thing. So if we want to go from moles of something to moles of something else, we use the balanced chemical equation. And so here the ratio is 1 to 1. So I'm going to go down here, and I'm going to plug a 1 and a 1, and notice what happens. SF6 cancels out, and so now we get 0.260 moles of S. Moles of S. Okay, so now we go up here. So what we know is that we have made 0.260 moles of S more than what we started with. So we have added that many moles because we've made it. Okay, and then we're going to add some number of moles on this side. So again, we're going to start with our first change box that we calculated, moles of SF6. Okay, and again, X-line, but instead of going to sulfur, we're going to go to fluorine. So we have SF6 to F2. Notice SF6 cancels out. The only thing we have left is moles of F2. That's how the units can tell you what the answer is, or can tell you if you're setting up the math correctly. So again, we go back up here, we look at the balanced chemical equation, And for every 1, remember, if there's no coefficient, for every 1 SF6, we make 3 fluorines. So for every 1 SF6, we make 3 fluorines. So we probably need to do this in the calculator. So 0.260 times 3. And so this is equal to 0.780 moles of F2. And that is going to go up here. 0.780 moles of F2. Again, we don't have to write units because we know that stoichiometry ICE charts are written using moles as the unit. So now 0 plus this, fill this out, this becomes fairly straightforward at this point, and 0.780. And now the good thing is we've done part B. So now let's look at part C. It says now we need to figure it out in grams. So in terms of grams, now we have to convert moles to grams. How do we convert moles to grams? We use the molar mass. So now we take the moles and we X-line it using the molar mass. So 0.260 moles of S of sulfur, X-line, and then moles on bottom, grams on top. Notice what's left is grams of sulfur. And so for every 1 mole of sulfur, we have 32 grams of sulfur. So 0.260 times 32, that is totally, oh, that says 8.32. I thought it said 0.32. I was like, that's totally weird. Okay, so now what I'm going to do is I am going to take this, I'm going to put 8.32 grams underneath it. I do the same thing for F2. Okay, so for F2 is 0.780 moles of F2, and we X-line it, and we put moles on the bottom, and we want to convert to grams. But here we probably should figure out what the formula, what the molar mass of fluorine gas is. So for every for fluorine, there's 2 of them in it, times 19. Again, that comes from the periodic table, and that's it. There's just 2 of those, so that's 38 grams per mole. So for every 1 mole, it's 38 grams. So we do 0.780 times 38, and so when we do that, we get 29.64 grams. So now we come back up here, and we go 29.64 grams. The funny thing is that we can't do a check. We can't do a check, at least right this second, for law of conservation of mass, because we don't have how many grams of this we started with. But let's add this up anyways, plus 8.32. Okay, so we get 37.96 grams. But guess what we can do to check? We can just do kind of a very straightforward one-step calculation. Okay, and we can convert moles of SF6 to grams of SF6. So that's what I'm going to do, because it's worth it to me to make sure that I have the right answer at the end, as opposed to getting all the points off at the when we grade it. So we have 0.260 moles of SF6, but we need the molar mass. So sulfur, there's 1 of them in this formula, times 32. And then for fluorine, you have 6 times 19. So we get 32, because 1 times 32 is 32, plus 6 times 19. And so we get 146. So this is 146. And the units tell us grams per mole. So we're going to X-line this. We get moles. we get grams, and for every 1 mole, we get 146 grams. So now we take this and we do the math, and we get 0.260 times 146, and when we do that, we get 37.96 grams, and lo and behold, here we got 37.96 grams. So I know that I did the problem correctly, okay? There's probably no way, if you do it wrong, that you're going to accidentally or coincidentally get the law of conservation of mass to work out. Even if you balance it wrong, it's just not going to work out correctly. So there it is. That is how to do problem number 2, and have a great day.